Okay, so we'll do the last part of the isolated horizons, and then hopefully also try to finish the dynamical horizons. Dynamical horizons is a rich topic, but we're just going to cover the basic things about dynamical horizon. So we're now ready to do the last part of isolated horizons, which is multiple moments. Okay. So as we sort of saw, that the idea here is that the isolated horizon represent a horizon which is in equilibrium, right? So it has the end point of the collapse. So in the case of the Vaidya space-time, for example, the collapse due to a null fluid, we saw that we got psi minus, and then the null fluid falls, and we got some null part of the singularity, and then space-time is part of the singularity up here, and then sky plus. And this is the event horizon, and we saw that here space-time is flat, here space-time is dynamical and curved because a null fluid is falling up here. So where I got here, this is a null coordinate v, and where I got some m of v for the perfect fluid, which is falling up here. And then singularity forms, and I got the horizon, and as we saw here, that the event horizon starts forming. In fact, in the flat space-time grows, then there's it's a null surface. Then there's a dynamical part, and then again it settles down. So this part is Schwarzschild, and therefore this is static, and therefore the event horizon here is a Killing horizon, and the area doesn't change up here. The event horizon, that is really constant up here. Okay. And then what we saw was that in fact we have what happens in this case is that, in fact, the marginally trapped surfaces start forming right here, and the surface, we're going to discuss this a little bit more. At the moment, just take for granted that this is really the surface which is R equal to 2m, and this m of v change is increasing, so this R is increasing up here as we go, and then the statement is that as it increases, then finally it just reaches constant, so this is smooth, but if m of v is smooth, this will be smooth. And then this part of the horizon, after the matter has all fallen in, so here is our matter which is falling in. And then to the future of that, what do we have? The part of the event horizon to the future of this is also an isolated horizon. So this part up here, from here to here, is an isolated horizon. So this is the end, when the black hole reaches the equilibrium, what we have is the isolated horizon. But as I told you last time, that you might have these isolated horizons forming. This is a simple case in which outside there is no matter, there are no magnetic fields, there is no accretion disk or anything like that. So therefore this really is just a Schwarzschild space-time, so this is a simple horizon that the structure we know. But in general there might be matter, accretion disk and so on, in which case the horizon is actually going to be not that of the Kerr space-time, or in non-rotating case, not that of the Schwarzschild space-time, but in fact you're going to have some distortions on the horizon. So in general, the geometry of the horizon can be distorted. And by geometry of the horizon, we mean the metric QAB and this rotation one form omega that I got up here. We're always talking about here the multiple moments of a VT isolated horizon. So the geometry just consists of this. Of course, we've got a null normal, which is given to us up to a constant rescaling QAB, which is sigma 0 plus plus, and this rotation one form. And I think we saw last time that, in fact, on the weakly isolated horizon, what we have is the wild curvature component psi naught is equal to 0 and psi 1 is equal to 0, and therefore, in fact, psi 2 is gauge invariant. That is to say, all we really have is L. To construct these quantities, we need to complete the tetrad, so we need to have a null vector n, and m and n bar. There is some arbitrariness in that choice, and that is what we mean by gauge. And the statement is that psi 0 is gauge invariant. If it is 0, then psi 1 is gauge invariant. If it is 0, then psi 2 is gauge invariant. And psi 2 is not 0 in the isolated horizons, and that is the quantity that we have. And then finally, we'll also see that, in fact, d omega is, last time I think we wrote it as 2 times dA omega b, which is just d omega, is equal to imaginary part of psi 2 times epsilon d. Right. So this is what we're seeing. Okay. So now, so you can see already from here, I've given you a hint before that omega is rotation bound form. So you will imagine that the information about rotation is in the imaginary part of psi 2, and I was telling you that that is correct. And the information about mass, if you like, is really in the real part of psi 2. So that is how the information is really distributed. So what we can do is we would like to define multiple moments. But of course, psi 2 and omega psi 2, real and imaginary part of psi 2, are just functions on this horizon. And in different numerical simulations, they will calculate these functions and they will be expressed as functions in some coordinate systems. In the 2 coordinate systems, it's not obvious to compare exactly what's happening. In other words, I got one numerical simulation gives me one space-time, another numerical simulation gives me another space-time. They started with physically the same initial data, and we would like to compare the structures of the final isolated horizon and see if they are the same or not. And to do this in a coordinate invariant manner, what we can do is define multiple moments. Now it turns out that even though you can define these multiple moments also in a case when the horizon is not axisymmetric, this is something relatively recent and has not been, not all of the results are in the literature. But the simpler case is assuming that in fact the horizon metric is axisymmetric. So supposing we assume that QAB admits a rotation killing vector. This is not a strong restriction in the sense that in the numerical simulation, of course, finally the horizon that you get is axisymmetric and it completely settles down. It is a Kerr horizon if there are no accretion disks. So therefore QAB admits a rotation killing vector field is an assumption up here. That means we got some vector field phi whose orbits are closed and leave phi of QAB equal to 0 on the horizon. So this is a statement, this is not a statement that the whole space-time is axisymmetric, it's a statement just that the horizon is axisymmetric. So in this case, it turns out that the geometry of the horizon, which means the metric and the one form, that information that we get up here, that information can be completely recovered by giving you a set of multiple moments. And the set of multiple moments are just, so the multiple moments are just numbers, right? Tower of numbers. And if I give you those tower of numbers, they don't refer to any coordinate systems. The statement is that you can reconstruct the horizon. And conversely, if you give me horizon geometry, then I can construct for you this tower of numbers. So how is this tower actually defined? So multiple moments. And the idea here is really, on the web page, I will give you, on the web page you already have a review article that was written by Badri Krishnan and me in 2004, so quite some time ago. And I've given you explicitly the sections that you should be reading, and those sections include one in which the multiple moments are defined. And also, there is a detailed paper on multiple moments, which was published just before, that is referred to also in this paper, or in this review paper up here. So how are the multiple moments defined? Well, the idea is really, as the detailed paper shows, that we take the idea straight from what we do in electrodynamics or electrostatics, if you like. It's rather in presence of stationary currents, right? So it's not electrostatics. There is also magnetic fields, but the magnetic fields are time independent. So let's say it is time independent solutions to Maxwell's equations. So in that case, we know how to define charge multiple moments, and we how to define the current multiple moments, and the idea is really taken from that. Looking at the horizon structure, you can associate with the isolated horizon a mass density, if you like, and an angular momentum current density. And the analogy is really with the charge density in electrodynamics in the time independent situation and a current density in electrodynamics. And if you are given the charge and the current density, then you can define multiple moments. And that's the idea that is taken over here to define it. But of course, in electrodynamics, we are working typically, of course, in Minkowski spacetime. And in Minkowski spacetime, you have got a flat metric. And the multiple moments, as you all know, refer to YLMs, right? Spherical harmonics. It's a spherical harmonic decomposition of the charge density and the spherical harmonic decomposition of the current density. But here we don't have a spherical, we don't have, in general, the horizon geometry may be distorted and so on. But there is a very nice result. So this is just a mathematical simple statement, which is, at least to me at least, at first was a little bit surprising. So mathematical statement. That given a two-sphere geometry, so given as two-sphere and a metric on a two-sphere, such that it is axisymmetric. So there is one Killing vector field. It's not spherical symmetric, it's axisymmetric. Then, using just the information that you have got this metric, and you have got the rotational Killing vector field, and the rotational Killing vector field, of course, given this metric, you can calculate the norm of the rotational Killing vector field. The twist of the rotational Killing vector field is 0, so you can calculate the norm of the Killing vector field. Just from this information, you can actually reconstruct, you can actually put on this S2 if you like a fiducial spherical metric. Given this, one can obtain, one can induce, one can define on this S2 a unique spherically symmetric metric. So one which has 3 rotational Killing vector fields. This Q0 AB is really constructed entirely out of the physical metric you have given me, which can have distortions, therefore is not axisymmetric, therefore it is not spherical symmetric. It is assumed to be axisymmetric. So what does it mean? It means that there's a Killing vector field in the d by d phi direction. So I got a sphere and I got a Killing vector field in the d by d phi direction. But in the theta dependence, I don't have any symmetry. So the metric can be distorted in the theta direction. Okay, it's not a spherical metric in the theta direction up here. Still it is a case that given this metric, you can uniquely define a spherically symmetric metric, which of course knows about this metric and knows about the intrinsic properties of the Killing vector field, such as where the Killing vector field vanishes, what its norm is, and so on. Yeah.
So I can think of this sphere as a rotational body beforehand.
Can.
Yeah.
I mean, you can think of the sphere as if you wanted. You can think of
if I would like to isometrically embed this 2-sphere into 3D space with the original metric, it would just be a rotational. Like it would be a body that is.
Yeah, this metric.
Exactly.
Like that, right.
And now this fiducial metric. What how do you choose it? Like what does it do?
Yeah. So the statement is that from the geometry of this metric, so you know its scalar curvature, you know and you know its scalar curvature basically, and which is invariant, which doesn't depend on coordinates at any point. And you are also given a Killing vector field, so you know the norm of this Killing vector field. So in particular, you know where this Killing vector field vanishes. Given just these 2 data, I can explicitly write down for you a unique spherically symmetric metric. So it is not, it's a mathematical construction. And of course, if Q happened to be spherically symmetric to begin with, then Q naught equals Q. Doesn't change. It's exactly the same.
So I'm somehow missing the point, because I mean, if I have a two-sphere, I can always write down a metric just on the manifold that turns it into a standard two-sphere.
Right, but there are many ways of doing it. Right?
Exactly.
You do it to one, and I make a diffeomorphism on it. So give me a two-sphere, you give a unit two-sphere metric of some radius on it, and I perform an arbitrary diffeomorphism on it. Then that's again a unit two-sphere metric with arbitrary diffeomorphism. The reason is because scalar curvature is mapped to the scalar curvature. So the scalar curvature of the old metric was constant, scalar curvature of the new metric is also constant. So the problem is, good you asked me that. The point is that we would like to define multiple moments, so we need some spherical harmonics. Spherical harmonics with respect to what metric? Well, I mean, Lucas says, just choose a metric, right? As two-sphere, I can use a unit two-sphere metric or a two-sphere metric of some constant radius on it. Just choose one and define spherical harmonics with respect to that. But the problem is that he chooses one, and then Emmanuel chooses another spherical metric. He just performs a diffeomorphism. So his spherical harmonics are completely different from your spherical harmonics, and there is no relation between them. So you would say, oh, this one has quadruple moment, and you say, no, it doesn't have any quadruple moment. All it has is octuple moment. So then there is not invariant characterization. So what we want is really use just the fundamental geometrical structure. This metric, it's really scalar curvature is what we are using very strongly, and we're also using the topology very strongly, and the fact that we have got a rotational Killing vector field. Okay. And the statement is that given this, there's a constructive procedure to obtain particular this metric. And this is a coordinate independent procedure in the sense that it's not that you give me this two-sphere in some metric. It says that, well, I mean, given axisymmetric metric, you can always do these things, or do those things. And at the end of the day, I'm producing for you a unique metric to sphere, and such that, of course, the phi of Q naught AB is also 0. So this particular metric, this particular Killing vector field is also a Killing vector field of this spherical metric that I'm talking about it. And it turns out that epsilon AB, the area to form of the two metrics is the same. These are just properties of that particular two spherical. So the statement is that you give me any possibly distorted metric. So in other words, you give me a possibly distorted isolated horizon, and I can introduce on it, just in an invariant manner, a canonical two-sphere metric. Now, if I got canonical two-sphere metric, then I'll be able to talk about the YLMs. So now we then introduce which are appropriately, as in textbook, normalized eigenfunctions of the Laplacian operator with respect to this metric up here, and the phi operator, basically d naught square. So d naught is a derivative operator of the metric Q naught AB, of this metric Q naught AB. So this times YLN is equal to the normalized, standard normalized constant, which depends on LN, times L plus 1 times YLN, and d phi of YLN, or if you like, d by d phi of YLN is equal to some other constant prime and times YLN. And you know that these are canonical, these are invariantly introduced up here. So we get these functions. This depends upon phi by phi. I mean, if you introduce a coordinate system adapted to the two sphere, then they will depend on theta and phi. And now the idea is to use this YLN to define the multiple moments. But multiple moments, what field do we expand out to define multiple moments? And then a very detailed analysis shows that the appropriate field is precisely this I2. It has exactly the same information as in electrodynamics you would have for, so to say, a mass density and a charge density. And this is done in detail in the detailed paper that I just mentioned to you, and which will be on the website for your reading material. So because of this, the statement is that now we got this YLN. So we just define the multiple moments. So we got, these are called the geometric multiple moments. And these are the real part, if you like. Oh, sorry. So these multiple moments in general will be obtained by smearing with YLN. But because we have assumed that the metric is actually axisymmetric up here, we will only get multiple moments corresponding to m equal to 0. Right? To go beyond m equal to 0 multiple moments is the more recent work. That is a little bit more technical, so that's why I'm not doing it up here. So at the moment, you're going to get multiple moments which are going to correspond to m equal to 0. So they are just y0, yl0 up here. And these are just defined to be the real part of multiple moments. So yl plus I times. So these are like the mass type multiple moments or charge density times multiple moments. And these are angular momentum times or current time. Multiple moments. And this is just defined to be equal to integral of just xi2 times y0 times d2v. And again, because epsilon is equal to epsilon naught, does not matter if you put here d2v naught or you just put d2v, is the same area element. So I'm just telling the final result, and the final result seems it's easy, and it is easy final result, and that is why people in numerical simulations actually can calculate this because they have psi2, they just calculate these multiple moments, and then you can compare. You got a simulation, you started with initial data, you thought it was the same, you said the black hole, they collided or there's a gravitational collapse, and then you got a final isolated horizon, and then you can compare and see if in fact you get the same answers or you don't get the same answers. If you don't get the same answers, then at least one of you is wrong, and therefore we had to sort of go and check what exactly went on. It's not an issue of coordinate freedom. Now I want to emphasize this, that in numerical relativity papers very often you will see pictures of the marginally trapped surfaces. These are all marginally trapped surfaces up here. And then you'll see the geometry to be very distorted, right? But almost every time it's a coordinate effect. It's just they've chosen some coordinate systems and they're plotting, for example, some functions in those coordinate systems, and they look distorted. Well, that's, in some other coordinate system they will look something else. Right? It's not yeah. So therefore the statement is that, but on the other hand, if you calculate these multiple moments, right, this L going from 0 to infinity, if you calculate these multiple moments, they completely characterize the dynamic. So that the theorem is that given a weakly isolated horizon leads to the mass type and the angular momentum types multiple moments uniquely. By uniquely, I just mean it does not involve any extra structure. It does not involve any choice of coordinates. It does not involve you to do something else. So I said axisymmetric. So the theorem is basically that given an axisymmetric weakly isolated horizon, you get IN LL uniquely. So that's just given to you. And then the statement is that once this is given to you, then you can reconstruct the metric and the omega A uniquely, of course, up to diffeomorphisms, isometry if you like, from IN and LN. So these multiple moments characterize the horizon geometry at the end uniquely. Now, in particular, what we can do is we can take the Kerr horizon, that is of interest, right? If there is no accretion disk outside, this horizon will be a Kerr isolated horizon. So we can look at what are the multiple moments of the Kerr horizon, and these have been calculated. I want to emphasize just one thing, which is the following. Okay, there's one point I want to make, but I think there's a question. Let me just answer the question.
I have only two questions. You're saying we can get the complete psi 2 just from the m equals 0.
Yeah, because it is assumed to be, the whole thing is killing vector field, right? So that's the statement. This is axisymmetric, right?
Oh, okay. Okay.
By assumption, but we would like to remove this assumption. For example, when the black holes collide, okay, the final geometry is axisymmetric, it's Kerr. But in the initial stage, it's not axisymmetric at all. And in fact, the angular momentum vector, for example, is not something that is sort of given to you. It's not only that its norm changes something. This direction will also change. It finally will settle down someplace, but everything will change. So how do you accommodate it? And this is a much harder question than this. This was not trivial either, but this is much simpler. And that has been, part of that has been answered, most of it, 90% of it has been answered in the paper 4 years ago, in 2014, with Miguel Campiglia and Samir Shah, that we are sort of told how to talk about this. So these multiple moments also in the dynamical region. The reason I'm not talking too much about it is because I've not done the dynamical horizons yet. So there is a framework for doing that, and the statement is that if you did it for the dynamical horizons, you will see how the dynamical horizon multiple moments settles down to the isolated horizon multiple moment ultimately.
And the other one is, are these spherical harmonics spin weighted, or are we just omitting it for now? No, they're like...
They're not, they're just ordinary spin, or ordinary spherical harmonics. They're not spin vector spherical. So, okay, so this is the basic thing. Now, the only thing that I want to sort of emphasize is the following. In Newtonian gravity and in time-independent electrodynamics, what is it called? It's called electrostatics and magneto something, where the currents are time-independent. Okay, stationary electromagnetic fields, right, where the charge and the current densities are all time-independent. It's stationary because there is current density. So the current density is something is happening in time, but the current density is time-independent, like a charge and current. So in both in that case and in Newtonian gravity, we only have mass multiple moments. Normally we don't talk about angular momentum multiple moments at all. But in electrodynamics, we talk about both the charge multiple moments and the current multiple moments. The charge multiple moments are like the mass, they are mass type, they are like ions, and the angular momentum multiple moments are like ion like this. So these will have the information about, local angular momentum density on the horizon, if you like. And this has the information about the local mass density on the horizon. Okay, so one remark. So in Newtonian gravity, we just have d squared of phi, or del squared of Laplacian phi, right? Laplacian phi equal to 4 pi rho. Always confused. Is this plus or minus in gravity? The Laplace equation in gravity, is it minus 4? Okay, it's
Plus what?
plus. Okay, thank you. So it's 4 pi rho. I mean, yeah, good. So we get here del phi is equal to 4 pi rho. So that's our Laplace equation up here. And what we can do is we can take from this rho, we can construct source multiple moments, right? For example, integral of rho dV is equal to mass. Then I can take integral of rho x dV, and that will be the dipole moment. And I can take the quadrupole moment by taking the second rank trace-free tensor. That will be quadrupole moment, and so on and so forth. But I can also take this phi and I can also expand it near infinity, asymptotic expansion. Right? And I will get something upon r plus something upon r squared. So I'll get here what exponent. So I'll get here partial expansion. And we can calculate the field multiple moments from this power series expansion. For example, the 1 upon r coefficient will be dictated by the mass. The leading order phi will be equal to, let's suppose phi goes to 0, that is our convention, that phi goes to 0. Then m upon r would be the first term. That m, the field multiple moment, the term which goes like 1 upon r, is a measure of mass. The term which goes upon 1 upon r squared is a measure of dipole moment, and so on and so forth. So there are both. So this is just a YLM expansion of the Laplace equation. Right? Just taking the YLM expansions, then you are going to get the solution to be equal to some radial function RLM times YLM, and you are just expanding out RLM. And the coefficient of YLM will give you some RLM, so will be some, they will fall off in certain rate. Therefore, I can look at those coefficients of YLMs, and they will give me field multiple moments, and I can just integrate the sources, and they will give me the source multiple moments. And the point is that because of this equation, we have a little theorem which says source multiple moments are the same as the field multiple moments. So for example, you can calculate the mass by integral of rho dv, or you can calculate the mass by looking at the expansion, 1 upon r expansion of phi, and look at what is 1 upon r term, and that will give the same. Okay, so we got these two kinds of multiple moments. And the two are equal to each other. But in general relativity, in fact in all non-abelian theories, you all know that the gravitational field itself is a source of gravitational field, right? Gravitational field also is a source of gravitational field. Gravity gravitates, right? That's the non-linearity of general relativity. Therefore, if you know only the source multiple moments, you would not know the field multiple moments. So these can be in general relativity. In general relativity, these can be defined. These are defined at infinity, and these are called Hansen or Garrosh-Hansen multiple moments. These are analogs of this. These are generalized to infinity, and these are called Garrosh. So they actually measure the multiple moment, if you like, of the field, and therefore, but the source for those multiple moments is not just the matter source, but is also the gravitational field which is there between the matter and infinity. So this includes both of those things. Whereas these kind of multiple moments, these are kind of typically not well defined or typically difficult to define. Beyond linear theory, beyond power series expansions, beyond approximations. In exact theory, it is not, it's very difficult to define. And therefore, when people talk about multiple moments, a lot of time in the literature when people say that, well, they would like to test no-error theorem. And for that, they would like to know if in fact the multiple moments are the field multiple moments at infinity that are the same as those of Kerr. Okay? But this is the field multiple moments. They don't tell us what are the source multiple moments, which are the multiple moments of the horizon. The field multiple moments include everything, not just what is at the horizon, but also outside the horizon, in particular gravitational waves and everything, right? So we have to be careful about when we say that when I'm testing general relativity, people just define these multiple moments from Kerr asymptotic expansion and spatial infinity, but is that what we should be doing, right? I mean, so this is, I mean, what exactly is the test that you're doing? What quantity are you calculating and comparing with the field multiple moments of Kerr? That needs to be understood in much, much more detail than is typically done. So this is the thing that I want to emphasize. On the other hand, you can, in the numerical simulations at least, you can just calculate these multiple moments of the final horizon, and these will be the analog of the source multiple moments. So horizon is an exception. Normally I don't know how to define source multiple moments. But for horizon, I do know how to define source multiple moments, and that is because of all these interesting properties. Psi 0 is equal to 0, psi 1 is equal to 0, psi 2 is gauge invariant. Given a metric, which is axisymmetric, I can define canonically spherical harmonics. I can do this decomposition. this is something that is true for a horizon. It's not true for a star. If you give me a star in general relativity, a random star in general relativity, it's not easy to define those multiple moments. I don't mean there are no attempts, there have been, but it's very difficult and there is no kind of consensus as to what those multiple moments are. But for the horizon, we can, which is, to me, very interesting. The sum of black holes are indeed rather simple objects. The horizon, we got multiple moments, and we can define them. This is what.
Is that related to it being a null surface?
It's related to everything, right? I mean, it's not just null surface, but it's an equilibrium. And all these properties are true, and there's a gauge invariant thing that you can extract. It is really the notion of weakly asymptotic horizon. That is why that notion is not so trivial. In the beginning, it seems, well, it's simple. It's just null surface, and the expansion is 0. But you add to it field equations and the energy conditions, and a wealth of information comes out, which is gauge invariant, which is not something that happens for a star, because such a wealth of information doesn't come out, and we can define these multiple moments in this particular way. So I think I really urge for those of you who do gravitational waves, when you talk about testing general relativity via no-hair theorem, please be careful about how that test is actually carrying out. When we say that there's only mass and angular momentum which defines these multiple moments, yes, but are we talking about the field multiple moments, or are we talking about the source multiple moments? The test that you're looking at is which kind of test is it? If it is, okay, so that this is something that we should worry about. And in particular, if there actually are accretion disks outside, so this is not just black hole collisions, neutron star collisions or something, then there is a 10% mass in the accretion disk, then indeed the multiple moments out at infinity would not faithfully capture just the Kerr geometry, will not capture the geometry up here, and you should not say, oh, now there is a violation of general relativity or something. You have to be much more careful in understanding if in fact there is a real violation, or you're just comparing something too crudely to arrive at a violation. So this is the thing that I would like to emphasize. Okay, so this is the end of the black holes in equilibrium, and then we start with the last topic. Are there any questions?
Just to what you just said, I mean, the horizon is great to do these computations, but to do a comparison with something that we measure here, that will always be more to the left side, what you're describing. So in what scenarios is there at least approximately a relation between the two, or is it really just a linear theory, like approximation where one can?
Yeah. So far, mostly what people have done is really looking at what is called quasi-normal ringing, which is really linear theory on Kerr space-time. And then there's some Moores, there's some eigenfrequencies with some appropriate boundary conditions where the waves are going out at infinity and falling into the horizon. And with this boundary condition, you get some eigenfrequencies, and these quasi-normal ringing tell you that the signal should be damped after the black hole is settled down and we enter the linear regime. Then you can look at infinity and the signal is damped. And then by looking at the damping, which will give you the imaginary part of the quasi-normal frequency, and the oscillations which give you the real part of the quasi-normal frequency, you can check if in fact that is the same as that of the Kerr space-time, or if it is not the same as that of the Kerr space-time. That is what people would like to do, people will do. This is difficult for some technical reasons, but that is kind of when people say testing Kerr, they are often referring to this. However, there are much more strong field tests of general relativity, which is really when the two black holes collide and a dynamical horizon is formed, which is our next topic, and the dynamical horizon is formed. Then something happens in this dynamical horizon. The multiple moments of this dynamical horizon are complicated. As I was saying before, the angular momentum vector is really not pointing in the same direction as time goes on. It might flip, it might do various things. And those things would also be registered at infinity. How do you transmit that information, which is happening to the horizon, to infinity, is a hard problem, but there are very interesting papers on it. Several numerical relativity groups are looking into this in detail. These are the ideas that I suggested some time ago about how what is happening to the multiple moment structure of the dynamical horizon could be registered in the radiation that goes out before the quasi-normal ringing sets in. That is to say, before we are in the linear regime, in the full nonlinear regime where the signal is strong. So this is something that is hot air. I mean, for me at least, it's an important and current area of research, and there is no conclusion, but there is an idea to do this. Any other questions?
Do we expect there to be like a one-to-one map of like multiple moments on the event horizon to those at infinity, or is that?
I think, as usual, one has intuition, but typically nonlinearity general relativity requires you to modify that intuition. So I would just say that to zeroth order, yes, I expect that. But I mean by that is to say, I do expect that, for the leading order things like quadrupole moment, octuple moment, and the angular momentum, dipole moment, angular momentum, quadrupole moment, I would actually be able to see what is happening in the radiation and what is happening on the dynamical horizon. But this could be a whole course, and that will be very interesting to do, but we're not doing that. And so I think there is a very nice project of actually constructing the waveforms which have this information. In other words, adding to the template of the waveforms further information. Typically, the templates of the waveform, they are obtained by the post-Newtonian approximation in the inspiral phase and the quasi-normal ringing from the quasi-normal thing. But in between, one is really numerical relativity. And there, the statement is that we don't have direct kind of physical intuition. We do have waveforms and we have developed some intuition, but not as detailed as we want. And this would be the way to get that very detailed information. So I do expect that there would be signatures of the time changing of the mass quadrupole moment and time change of mass octuple moment and time change of mass angular momentum dipole moment and of angular momentum quadrupole moment. These are the leading terms. Those you should be able to see in the waveforms at infinity. Exactly how, etc. is difficult. There's going to be a retarded instant of time. You have to do the matching correctly. So people in numerical simulations some groups are engaged in trying to do this. There are some preliminary results, but I don't think yet anything is really definite. Okay. So the last part now that we talk about is, as I told you, that what we did in great detail is really the Schwarzschild-Kerr metric and their properties and their geometry and their physical properties. And then we also did in some detail mathematics of isolated horizons. The reason is because we're going to use it again at Scry. That's the reason why we did it in much more detail than we can, or that we needed to for that purpose. And now we have a lot of intuition here. And now the statement is that, then I went fast, and I just told you that multiple moments can be defined, that psi 0 is 0, psi 1 is equal to 0. These are all in papers, you can read it, anybody who is interested. But it's important to have this global structure in mind, and the global structure that you have in mind up here is just that psi 2 is gauge invariant, and it has non-trivial information about the distortions and non-trivial angular momentum structure of the horizon itself. If you like, these are the source multiple moments that one can use. So that's what we need to know. All right. Now what we want to do is the last topic, which is dynamical horizons. I mentioned to you that if you have any ideas about how we should divide the rest of the time, this discussion has taken us 3 lectures more than what I had planned for black holes. So we'll have to cut 3 lectures either in the cosmology part or in the gravitational waves part. If you have any suggestions as to what your preferences are, if there is overwhelming preference, I will do that. If people don't mind, then I will just follow my own intuition as to what to do. It's not too bad. We're 3 lectures behind, but it's not too bad because I purposely spent a lot of time doing Scry, null infinity, which otherwise we would do in gravitational radiation part. So we already put Scry as well as this isolated horizon geometry things, which we'll be able to take in. So therefore we'll be able to go a little bit faster. So we're not really 3 lectures behind, but we are a little bit behind. So please let me know what your preferences are. So next topic is going to be gravitational waves, because we'll continue with this naturally. Cosmology is kind of the other most important applications of general relativity. So please let me know after the class or send me an email. Okay, so dynamical horizons. So the idea up here is precisely what I was telling you about before, namely that what we're interested is really when, for example, the black hole actually forms, or when 2 black holes collide. Well, when they collide, common marginally trapped surfaces formed, and then you can stack those marginally trapped surfaces on each other. In terms of signal, it's not very long. It's typically 2 cycles or 2.5 cycles that in fact some nonlinear dynamics is actually seen at infinity. Okay? It's only 2. And then there's a quasi-normal ringing period, which is also roughly 2 cycles at the end for the black hole collisions. Only about 2 cycles at the end for quasi-normal ringing that is seen. So it's amazing that we have to try to extract all this information out of these 4 or 5 cycles that are relevant. Until then, it's really the inspiral phase, which is post-Newtonian approximation, and full nonlinear relativity is encoded in this few cycles after the common marginally trapped surface is formed. So here's a simple example, and this is too trivial, but that's why we can draw on the board, we can analyze in great detail. And this simple example is that we send in this null fluid, right? It's just a null fluid. So what I got here, the metric, I think I wrote down last time. So the metric here is dA squared is equal to minus 1 minus dA of V upon R. So it looks like Schwarzschild metric, but it has this extra term. Let me get this sign right. I think it is. No, I don't know. It's either plus or minus the next term. Plus. Okay. Plus. And this satisfies Einstein's equations. The Einstein tensor is equal to 8 pi times g Newton times TAB. And TAB, actually this way put equal to 1. And TAB, otherwise I should put here 2gm. And then TAB is just given by m dot of V. So it's just dm by dv upon 4 pi r squared times V. Okay, so this is the metric we got. In the past, in this region, m of v is 0 up to here. This is say v equal to v naught. This is null fluid, if you like, this is just a coefficient, right? I just define this coefficient. But it then turns out to have that it enters in the metric by m of v, and so therefore you can think of it as a mass at that retarded instant of time. So I get this one equal to 0, and then m dot of v is equal to 0 for all v. That's 0 for all v greater than v1. So this is our v1. So to the future, m of v is just constant, and therefore the metric, if this is constant, is just the Schwarzschild metric. Therefore we got the Schwarzschild metric, and therefore we got the sandwich, flat space-time and Schwarzschild space-time with a dynamical null fluid which is actually falling across. All right, we've done it several times. I just am reminding everybody of this. So now what we can do is, in this geometry, it's spherical symmetric geometry. Right? It's completely simple. And therefore what we can do is we can find out where are the marginally trapped surfaces. And for simplicity, if you take a random marginally trapped surface, right, which is not spherical symmetric, the problem is hard. It's much harder than I thought. People have by now done it, but it's hard. But on the other hand, we're just looking at spherical surfaces. R is equal to some constant 2 spheres. Around 2 spheres. Okay, so look at this R equal to constant 2 sphere for various values of V, and you will find for various values of V, and you ask when is it going to be a marginally trapped surface? So we are asking when is it true that theta sub L equal to 0, where L is the null normal, which is outgoing, right? L is always an outgoing null normal. That's what. So L future directed outgoing null normal. Everybody okay with this? That's what we mean by marginally trapped surfaces. Yeah? So given any two sphere, there is going to be an outgoing null normal L, there is going to be incoming null normal N, and we look for that. And your homework problem asks you to do this and to show that in fact this is satisfied precisely for R is equal to 2N of R of V. So you fix a V that will give you some, that will give you a two sphere R of V, and then when its value is equal to 2NV, then it is marginally trapped surface. For larger values of R, for that V, you will again get some two sphere, but in fact that two sphere will be not trapped. And for smaller values of R, smaller than what the mass is at that instant of time, you will get trapped surfaces. In other words, the expansion of L is actually negative. So then we can ask, what is the world tube? What is the curve in this RT plane or RV plane? What is the curve which corresponds to that corresponds to marginally trapped surfaces? What is the world tube of marginally trapped surfaces? What is the surface that you obtain, 3D basis surface you will obtain by stacking these marginally trapped surfaces? And I already have sort of told you before, just the beginning of the class today, that in fact what you get is marginally trapped surface starts forming here. To begin with, it has M of V. So at this point, M of V is just 0. So to begin with, it starts with 0 area, if you like, and it grows until we get here the area. So here, here M of V1, that is constant, and then throughout here, the mass is just M of V1, that mass does not change. And therefore, during this region up here, the radius of these marginally trapped surfaces grows from 0 to M of V. That's what is growing up here. So this is the marginally trapped tube. In other words, it is obtained by stacking these marginally trapped surfaces, and you can quickly check that it is actually space-like, and R is growing. R grows from 0 to R is equal to MV of V1. At any given time, R is equal to MV, so it grows from 0 to the maximum value, which is M of V1, and then it stops, and then it's the isolated horizon. So this is the dynamical part that we are looking at here. So what we are interested now is really dynamical horizons. So we are interested in these world tubes in which the marginally trapped surfaces, the area is not fixed. The area is growing or is decreasing. So that's what we are interested in. So we make the definition of what a dynamical horizon is. Again, it looks extremely simple, just like for the non-expanding horizons. So a dynamical horizon is, now for classical relativity is always going to be space-like. So I'll just put in space-like here, but you don't need it in the definition. Is a space-like 3-manifold. Let's call it H, which is foliated. Slice, foliated is space slice. By two spheres. Which expansion of theta, outward null normal is equal to 0. So that's what we are looking at. And we will be only interested here in the dynamical horizons which are future. Remember, in the case of isolated horizon, we are a black hole type isolated horizons which are future horizons, and white hole type isolated horizons which are past horizons. And they can be distinguished from the fact that the future directed N vector field that we got here, their expansion for the future horizons is negative, and for the past horizon is positive. That's how we distinguish. And for the dynamical horizons, we are only interested in the future horizons which are formed mathematically, we'll also look at the past horizons, and in some cases it might be interesting, particularly in quantum considerations. But here again, for classical ones, we are going to look at d plus of n, which is this method here, where LA is outward pointing, future directed, non-normal, and A is inward pointing, future directed, non-normals. And the example is Vaidya space-time that I just told you. The surface, which is R of V, is 2M of V. This is the surface that we are looking at. The space-time gives me the function M of V, and I look at the values of R at a given instant of time for any V which agrees with this, and that will give me a curve, and that R of V is equal to the pre-specified value is this space-like curve, and this is the example for 0 is less than, sorry, for V naught is less than. So that is a dynamical horizon. Again, the definition is very simple. It's quasi-local. Again, we can be very sure that in this room there is no dynamical horizon, right? There's no, we are not sure that in this room there is no event horizon. There probably is actually some gravitational collapse which is going to happen a billion years from now. But we know that there is no dynamical horizon in this room, and so that's good. Okay. All right. So that's a very simple definition. And now, what are we going to do with this dynamical horizons? And now something very interesting happens, something that I had been not expected at all. It was a total surprise for me. For event horizons, even if you ignore all the teleological properties, the fact that it's too global and so on, you can of course accept it all and everything. What is kind of the main key result for the event horizons that I know, about the properties of event horizons that I know? And as far as I know, there is one key result for event horizons, which is the Hawking's area theorem. And Hawking's area theorem told us that the area of the event horizon cannot decrease. Right? If, under some assumptions, which are physically reasonable, the area of the event horizon cannot decrease. So this is the statement. But on the other hand, Hawking's theorem doesn't tell us quantitatively how much the area increases. I give you a physical process and I want to know how much does the area increase. So at first, when I was a student and so on, I thought that, okay, Hawking has done the first step. The second step would be to actually say that, well, if so much matter fell in, then the area increases by this amount. If so much gravitational waves fell in, then the area is increased by this amount. And that's what we would like to show. But this example shows that this is hopeless. Because the area is increasing here. Area started from the event horizon from 0, and it increased, right? To here, 2m of v1, it increased. But already from here to here, it increased in the flat space-time region. We can just calculate what this area is right up here. It is a null cone, so we can calculate the area up here. And nothing is happening here. It's flat space. There is nothing falling across the event horizon, neither matter nor gravitational waves, because it is flat space, and therefore it's clear. This one simple trivial example makes it clear that you could never prove a physical result which says that the area of the growth in the area of the event horizon is because there is a flux of something falling into the black hole. You just can't do that. This makes it clear. But to me, the big surprise was that for a dynamical horizon, there's a law about how the dynamical horizon grows. And it grows precisely by the falling of matter and gravitational waves across the dynamical horizon. So to me, this makes it much more physical. A, because it's quasi-local, and B, because there is a quantitative law which tells us how the dynamical horizon grows. Whereas for event horizons, we only have a qualitative law which says that the area of the event horizon cannot decrease. So it remains constant or it increases. Please ask any questions you have. Just a second.
So I get confused between the dynamic horizon and the MTS.
Marginal trap surface.
Yeah.
Okay, so confusion is about marginal trap surface and dynamic horizon. A marginal trap surface is a two-dimensional surface like this, such that the expansion of the outward null normal is 0. Dynamical horizon or isolated horizon is a three-dimensional surface. It is obtained by taking these marginal trap surfaces and stacking them, putting them on. So for example, each of these things up here is a marginal trap surface. This is a marginal trap surface. This is a marginal trap surface. These are all marginal trap surface. This is a two-sphere, right? It's RT plane, so it's a two-sphere. So each of them is a marginal trap surface. I have stacked them on top of each other to obtain a three-dimensional manifold. Three-dimensional manifold in space like here and it's time like here, and it's null here. And that is the difference between the dynamical horizon, between the dynamical or isolated horizons and marginally trapped surfaces. Is this clear?
I pretty much the same question. Non-expanding horizons, only the difference is time. It's null instead of space-like.
Yeah, and the non-expanding horizons, I did not explicitly ask this, but if you wanted a future non-expanding horizon, you do ask this.
That's what I was wondering. So,
the only difference is this, exactly.
Because it's in parentheses, so it seems like unimportant, but it seems to me that it's the actual difference to what we have done before.
Right, yes. So the point is that, no, that is absolutely right. So the statement is that, let me just put space like here. The real way to do it is to talk about marginally trapped tubes. And they are not space-like. It's a three-manifold such that this is true. Or if you like a future marginally trapped tube is this. If it is null, it is an isolated horizon. If it is space-like or time-like, then it is a dynamical horizon. And then one should always talk about a space-like dynamical horizon and a time-like dynamical horizon. But in numerical relativity, but in classical general relativity, we don't, time-like dynamical horizons are not of interest. What is of interest is only the space-like. So we abbreviate it and just call it, dynamical horizon. But strictly speaking, we should say a space-like dynamical horizon is a space-like three-manifold, etc., etc., and a time-like dynamical horizon, a time-like three-manifold such that this is true. As we will see in a minute, that in fact, this space-like is important because this is what tells you immediately that the area grows. So if you just do that, if you have another question.
Yeah, this is the one thing I don't think I have the intuition for it, but I feel this thing is actually growing compared to the non-expanding horizon, right? And we still say theta, like the
right.
So are we getting to that exactly right now?
Yeah.
Oh, okay.
So what is happening is the following. So I can do more mathematically, but I'll just do it physically by just restricting myself to space-like ones. I can allow time-like, space-like null and say what is happening simultaneously, but it gets a little bit too abstract. So let me just restrict myself to space-like. So what does this horizon look like? So it's a space-like manifold, and we can write down a space-like manifold just like a plane up here. This is perfectly fine. But for your intuition, it is good to write it as a hyperboloid, right? You take Minkowski space, just this is a side remark. You take Minkowski space, maybe we want to take two-dimensional Minkowski space, just for sake of simplicity. So this is T and this is say Z. Just two-dimensional Minkowski space. Then the null cones are these null cones. So the vector here is really this outgoing. So L dot L equals 0, and this is incoming. So N dot N equals 0. But I can look at unit time-like vectors, and the unit time-like vectors will give me a hyperboloid. So this is tau. And tau A is equal to -1. Since the normal is time-like, is inside the light cone, it is clear that this object is space-like. Right? This object is space-like. So this object and this object, this is also space-like. They're both space-like objects. Intrinsically, this is intrinsic. Okay. There's no really, in terms of space-like I could either look at it or look at it. But dynamical horizons visually or intuitively are better be thought of as this object. This is what in quantum field theory you call mass shell, right? In momentum space, k mu is equal to minus mu squared. This is the mass shell that we're talking about here. So here I put more 1, but I could put another constant up here. So this is a mass shell that we got up here. And that is space-like. So now the statement is that if this is happening, I can look at z equal to constant surfaces. I'll be done in 1 minute. I can look at z equal to constant surfaces. So this is t equal to 0. This will be t equal to 1. Sorry, t equal to constant surface, not z equal to constant. T equal to 2. So these are surfaces. Time, usual time is passed like that. So even though this is space-like surface, right, you can think about time evolution in this sense. If you are intrinsic in the space-like in the surface, then there is no time evolution because all the direct, even if it was 3-dimensional, if this was not z but this was x, y, z, right? I got a hyperboloid like that, and intrinsically there is no time evolution because every direction is the same, right? It's this space-like direction. There is no time here now. But embedded in space-time, I can cut it by this standard foliation, and I can think of this as being time evolution up here in this surface up here. And you can see here immediately that what is happening is that in fact, as you go, right, the area of these two surfaces up here, these two if I was in 4 dimensions, then these will be two surfaces up here. The two surfaces here are 0 area, and this area is growing as you go down here. So here area grows. So intrinsically in the space-like surface, all directions are space-like. So there's no, in that sense, there is no time evolution notion. The time evolution notion comes because you embed this in space-time, and you look at some say as in this case flat spaces, flat 3-dimensional planes, or in general you can look at Cauchy surfaces which intersect this hyperboloid, and then you will see that the area is increasing. So this object up here is like the analog of the dynamical horizon. You think of the dynamical horizon in this way. You think of the dynamical horizon in this particular way. This is confusing because when I first talk about dynamical horizon, and I give a lecture to mathematicians, right, in one of the German Black Forest mathematics school up here, and they were all these mathematical relativists, right, very leading ones, and they kept saying, but how can area change in time? It's a space-like surface. How can area change in time? It's a space-like surface. And the real point is up here is that, of course, intrinsically there is no notion of time, but when it is embedded in space-time, the area is actually changing because it. Okay, so all these mathematical relativists, very distinguished ones, they felt that, well, I mean, if the area is increasing, it should be a time-like surface. It cannot be a space-like surface. In a space-like surface, the area cannot increase. And the point up here is that, yes, it can increase. And this is a very trivial example. And this mass shell, in fact, is a canonical way to think about dynamical horizons. All these things that I'm drawing up here, if I were to draw in space-time picture, they would look like, it starts on, yeah, that one actually does start with 0. And it grows. If the black hole collisions occur, then the dynamical horizons just starts with some initially area. This is the first marginally trapped surface that is formed, if you like, which encloses both black hole, common marginally trapped surface, and then the area of this marginally trapped surface grows, and that is the dynamical horizon, which is space-like surface. So this looks null, but I don't mean to make it look null. This is too close to. This is supposed to be. It's supposed to be hyperbolic. Okay. So let's stop here. The homework is due next Wednesday, and I'm almost due with my reports, and so I'll start grading hopefully later today.